Okay, everyone, we're going to get started with Passing Exceptions 101 by Amandine Lee.
Hello. So this talk is intended for people who are writing or wanting to write larger scale Python programs and want to think about exception handling and how to deal with error in the context of those. So in lieu of introducing myself, I'm going to give the context for why I decided to write this talk. I first began learning Python at Research Center about 4 years ago, summer of 2013. And I was interested in learning how to write idiomatic Python at the time and learn about best practices and style and things like that. I've been writing Python almost every day of my professional life since then. I worked at Juniper Networks for a while. Now I work at Dropbox. We have millions of lines of Python code. So I've seen a lot of examples of Python. For the last year or so, I've been doing release engineering for the desktop client at Dropbox, which is everything that takes code from an engineer's computer and packages it up, allows it to be in the same repository, and then turns it into an official version of the desktop client. And the thing about that is that last summer, I was given the task of taking a script that was designed to kick off making new official builds that kind of ran outside the context of the rest of Python code at Dropbox, and make it into a reliable service that could be run without anyone looking at it. So previously, an engineer would sit down and run this, and if it failed, they could babysit it. But we wanted to turn it into both a library that could be extensible, but also something that could run completely in the middle of the night without anyone looking at it. And when it came to exception handling especially, I found that it was kind of at a loss. There are a lot of things it depended on that could fail. There are reasons that it could exit early. I wasn't sure whether to write my own exception classes or use the built-in ones. So when I began writing this talk and thinking about the subject, there are some questions I wanted to answer. The first was, how do I make sure my code is reliable and correct? So it does what it's supposed to, and it doesn't crash arbitrarily. But also make sure it's readable and maintainable so that someone else could come along and edit it and not introduce bugs by accident and understand what it was trying to do. Questions I'm not trying to answer this talk include exactly how exceptions are implemented in Python in the language. Sounds very interesting, there's just not time. And what the performance trade-offs are for different patterns in Python when using exceptions. So to start off, I'm going to go over exactly what exceptions are in Python and how they're generally used, just to make sure that we have the same grounding. This is a set of the basic things that you'll see every day in exception usage. Alex Martelli did a talk last year that talks about other awesome tactical things you can do with exceptions, like syntax you may not know about. But this is the most common set of stuff. And what I want to emphasize is that exceptions are objects that, when paired with the raise keyword, cause the normal forward program execution to stop, and instead launch through the stack of callers that were above that function. So in this diagram here, you have all these different functions that are calling each other. Function D raises an exception. It'll travel up the stack, collecting a traceback, until it finds a try except handler that's relevant to itself. And you know it's relevant because except is followed by either a set of classes that are exception objects, or only one, or none at all, which implies that everything is caught. And it has to be either that exception or one of its parents in order for it to be relevant. And then from there, execution continues within the try except block. You can also do things like make your own subclasses. So this is an overview. Python has a bunch of built-in exceptions. This is the hierarchy, as best as I know, from Python 3.6. What I want to emphasize with this is that exceptions are used for a pretty wide variety of things, and not all of them are errors. I'll try to use those terms not interchangeably, but it's hard. So base exception is the grandparent of everything, and it has a few special children, which are mostly things that use that launch through the call stack thing to exit the program or exit the section of code completely. And then everything that's an error tends to be, or is, a child of exception. And they're often grouped together by similar types so that you can use that cool except general thing. And the names of the exceptions give you a hint as to what their purpose are. It's exit, or it's warning, or it's error. They all have the same underlying behavior, but that's implying the meaning. So next up, I'm going to take an example. This is paraphrased from actual code I looked at work last year. What the example does is take in a path and then open a file of that path, JSON decode it, and assuming it's a dictionary, read the value of ID and return it. If a key error is raised because ID doesn't exist, it returns none instead. So as I'm going through the different iterations of this example, I'm going to talk about the two things that I cared about at the beginning, the readability and the reliability of the example. I think this version does a really good job of readability. I certainly understand what's going on. But in terms of reliability, I don't really have any clues as to the context in which this is being run. And I'm really not very confident it's not going to crash arbitrarily. I can think of a lot of things that could go wrong. If there isn't a file at that location, for example, it's going to raise a file not found error. If it's not actually valid JSON, that will raise a JSON decode error. Maybe it's not actually a dictionary, for example. So I'm not totally confident this is going to fulfill the reliability requirement that we had. I'm also going to look at exactly why exceptions are used in the different patterns that we see. And this one, we had that key error, and it's indicating that something exceptional happened, which may seem obvious. Most of the time, we expect that an ID will exist in the dictionary, and some of the time it doesn't. And it's like having a special path for that purpose. So in an effort to sort of up the reliability quotient, we could do something like this, where we enumerate all the possible errors that we can think of, put little try except handlers around the relevant parts. Ultimately, what those different problems I talked about usually translate to if someone did not format the data as I expected to. So maybe I'd raise my own special exception class, malformed data error, and sort of expect my caller would know to reformat the file afterwards. So in the readability side of the equation, I think this is not doing as good of a job. There's certainly a lot of new clauses. I don't necessarily know from looking at what this is doing, because it's sort of obscured by all those try excepts. And in terms of reliability, I'm actually not 100% guaranteeing this is going to run all the time anyway. There are things that I didn't anticipate that can always go wrong. For example, if the disk isn't available right now, I think that raises an OS error which isn't captured by any of these exception handlers. Also, I think the readability is marred a little bit by the fact that we're using exceptions for really two different things. So sure, the absence of a key and errors happening in the other parts of the system are both exceptional, but the first one is something that we really expect. This function anticipates some of the time the key ID doesn't exist, and so it's using the key error as control flow, just going a different path down the normal execution of the function. And then we have all these other sources of error. Things that we don't really think are going to go wrong and can't handle locally in this function. And I think these are fundamentally different. So next thing I might try to do in order to boost the readability is to have a very general try except with everything in it. In order to solve the problem of using exceptions for two different purposes, I can use data.get instead, so key error isn't raised, and attribute everything else that could go wrong to this malformed data error concept that I had earlier. But if I were to run this, it's actually going to raise a malformed data error every single time. So it's not passing the reliability test. It's doing pretty well in readability, understand what's going on. But that general try except is obscuring the fact that I accidentally put an S at the end of loads. JSON.load operates on a file object. JSON.loads operates on a string. And so it's going to raise a type error and then translate that into a malformed data error every single time I run this function. It's not going to do what it's supposed to do. So we have now control flow exceptions, unexpected external error, things happening outside the scope of the code I'm looking at right now. And then we have bugs in the code that I'm looking at. And I think these are all pretty different. So I could keep going through and altering this and trying to evaluate it, but I think it's important to be a little bit more systematic about exactly what the different types of exceptions are, and therefore what we do with them. So I'm going to go through the list and look at what I think about each of those types of exceptions. When we are talking about control flow, the problem with using exceptions for control flow, though it's perfectly valid Python, is that you actually have to contain more information in your brain as a programmer looking at the code in order to understand them. You already have things like function calls and if and else and for loops that do a pretty good job of control flow. When you introduce exceptions, you don't really know at what layer of the stack they're going to be caught. So if I'm writing a try except handler, I don't know if someone below me is going to do the same thing, and I won't see the exception I expected. If I raise an exception, I could think that someone's going to catch it, but maybe it'll just bubble all the way to the surface and cause the program to crash. So if you're thinking about using an exception, I think the first step is to think about whether you actually expect this exception to happen, in which case you might consider using a different syntax in order to achieve your same goal. Some of the time you do need to actually jump the entire stack. All of those exits, for example, are like pretty valid reasons of using control flow, but they needed to go through everything and like exit the entire program, and so they can't do sort of forward execution. And then you will see exceptions used for control flow in other people's code and libraries you use. And this is inevitable, but sort of like understand that they're there. And then if you have a choice in using an API two different ways, one of which is control flow exceptions, and the other is sort of more standard execution, you can try and avoid provoking them to avoid this error of like exceptions going possibly anywhere in the call stack. I'm going to skip ahead one. So talking about number 3, bugs in my own code. If you type in invalid Python syntax, it's going to raise a syntax error in your interpreter, and there's not really a whole lot you can do about that. And I think this is actually a pretty good demonstration of what we should do in order to like alert to bugs in our code. You should raise errors super early. So this is, I don't think you can even catch a syntax error in the interpreter, I'm not sure. And other ways of raising errors early is using things like type comments in combination with static type checking, called MyPy, which my coworkers David and Yuka will talk about tomorrow. Or other forms of static analysis. So you're running something over your program before you execute it, which is useful if the exact code you need to execute has a lot of requirements, for example, is hard to run. And I think that PyCharm is like a really easy way to get a lot of static analysis benefit just by downloading a program. It will indicate common mistakes to you, and we inevitably write sort of typos and very small logic mistakes in our programs. Sort of bugs should also be omitted exactly where they came from. The syntax error here has an arrow trying to indicate what line. It's not always perfect, but it's trying to show you exactly where to look when you're debugging. And hiding things with really general try except handlers can obscure this. You end up pushing the bug somewhere else in the program, especially if you do like a try except pass. Probably you're leaving something around that is not correct, and an exception will just be raised later on. Also good to communicate the context of bugs. Stack traces are really great. You can log them. Or you can also add other information you can do custom things with exceptions if you want to, or just general print statement debugging. Then when we talk about unexpected external error, there's kind of a fork in the road here. Of the things that I named, some of them are problems with the things that are calling my function getID. Maybe they didn't even pass in a string for the path. Maybe they didn't set up the JSON dictionary correctly. Or they could be problems with the callers that I'm relying on. So my disk is ultimately something I'm relying on. If it's failing, my caller, or the callee, the thing I'm calling, is failing. Same thing if the JSON library suddenly has a new bug in it and is raising an exception. So when we're talking about this like callee-caller distinction, I think it relates pretty cleanly to design by contract, which is a concept introduced in like the 80s and 90s by someone named Bertrand Meyer, which talks about writing components of programs as if they're a contract. And the basics of a contract are that there are two entities. There's a client and a supplier. Our supplier is the function, the client is the thing calling it. And what design by contract says is that if the client supplies preconditions, if it sets up everything for success, then the supplier must fulfill the postconditions. It must, deliver the thing that it said it was going to deliver. If the preconditions are not met, it has no guarantees. And if it can't fulfill the postconditions, then it should raise an error and indicate that it failed. In the meantime, though, the client and the supplier may fail the contract, but everyone must maintain invariance for the program to keep executing. So invariants are things like list size has to be at least 0, your bank account has to at least a positive amount of money in it. Depends on the context, but they're things that would cause the sort of physics of your program to completely break if they don't exist. Our example doesn't really have one, but when writing things according to design by contract, you're supposed to include these items in sort of your contract. A bunch of them are things that you will see in standard Python docstring styles. So input and output types and values and what they mean, the things that are raised, side effects. And then the last 3 are things that are more novel when it comes to design by contract, which is our preconditions, postconditions, and invariants. So the language Eiffel was designed by Meyer to explicitly encode the ideas of design by contract. And it has these keywords require and ensure, which sort of automatically assert that the preconditions and the postconditions are met, and same thing for invariant. But we're at a Python conference, so we can't exactly use this language just out of the box. So I'm going to look at exactly how we can apply design by contract to Python specifically. The first question is, who is going to do enforcing of the contract? Eiffel does it automatically, but we in Python sort of have to choose exactly when we're going to raise an alarm that a contract is violated. Don't look at this example too long. It's clearly very long. It fails the readability test. It's trying to check everything at every single point according to the contract. And this is just our supplier. If our client were implemented, it would probably duplicate a lot of the same checks if we were to be very, very careful. And I'm not really sure that it actually wins anything in terms of readability or in terms of reliability either. I don't know if I've enumerated everything because I can't really read the function anymore. So when I went to write the final version of this code, I thought about it in terms of what would help someone actually attribute a breach in contract. And most of the time, the bugs that are raised, or the exceptions that are raised that I talked about previously, do a pretty good job of showing you what's wrong. So if the JSON decode error happens, then I'm pretty sure that means this isn't a valid JSON encoded object. I can look at this docstring and see that that is a precondition, and therefore it is not the fault of getID, it is the fault of the function calling it. One exception is that I did include this assertion at the end. My postcondition, and by the way, you can use type commenting to be really explicit about the input and output types, is that the user ID is expected to be either none or an integer. I actually didn't think about that until I wrote the type comment, so it's a super useful way when you're documenting to think about exactly what the contract of your function is. And so since I have no guarantee that I'm reading this thing from the disk, that it's actually going to be an integer, I'm adding an assertion to make sure that it doesn't sort of happen the next layer down, that someone expects an integer and then gets a type error to try and attribute closer to the source of the breach. So everything we've talked about so far is sort of assuming that you're just letting all of your exceptions bubble all the way to the surface. And practically speaking, this isn't exactly what we want to do. Oftentimes, we want to recover from error that's happening, and we want to do so intelligently. Here's where I started looking at a bunch of other languages and seeing how they handle error, and I think they're kind of informative. So there's a few basic ways in which languages have opinions about how error is communicated and handled. First off, there's error codes. Languages like Go do not have exceptions. They only allow you to return special values or just completely crash the program and panic. And you can do this in Python too. Plenty of times I've seen code that either returns like -1 or none or some other special value to indicate that something unique has happened with a function. Not unique, but something that possibly is different or erroring has happened. There's also checked exceptions like Java or Swift. And these are statically typed compiled languages where they're explicitly put into the function sort of declaration. And then if you don't catch that exception the next layer up, the code won't compile. There isn't really an equivalent in Python because it's interpreted. But oftentimes when you are looking at docstrings and trying to enumerate every single raised exception within there, you're trying to emulate a little bit of the checked exception idea. Then there are unchecked exceptions, which is the Python idea, which is exceptions can be raised at any point in time. There's no explicit declaration of them, and that when they're raised until they're caught, or they bubble all the way to the surface. Finally, there's abandonment. So a lot of the ideas in this section of the talk came from a blog post by Joe Duffy about his experience working on Midori, which is language designed for operating systems at Microsoft, and it has a dependency on being really performant. So their philosophy, and also in sort of more common language like Erlang, is that if something goes wrong, you should tear down the entire process and recreate it from scratch. And they have ways of doing this really lightweight so that it is performant. Often this is used in combination with things like error codes, but if something is like pretty bad, then they assume that your process just should not stick around anymore. It's like keeping something living that you can't functionally execute anyway, so you might as well, instead of doing this whole dance of like trying and catching and everything, just tear down the process and start from scratch. So to look at how Golang does this, we have, by convention, the last item in a function signature when it's returned is the error code. And it's just a lightweight wrapper around strings generally. And then since it's compiled language, if your function returns an error, someone at least has to assign that to a variable, and then you don't really have to do anything with it. But it at least forces the programmer to think about the fact that an error could be returned and whether it wants to pay attention to that. In the checked exception example, like in Java, also both of these are languages I don't write very often, so there are probably problems with the code samples. The function signature includes our malformed data error, and then since both opening a file and parsing JSON, according to their signatures, potentially raise exceptions, I have to have that try-catch in there, or it won't compile either. I think this actually looks a lot like our second example in Python. It's trying to be really explicit about all the things that could go wrong, but even in Java, there are things that can go wrong that we don't expect. Runtime errors can always be raised, and that still requires the programmer to keep that in mind rather than having it written out explicitly. So next, I want to talk about what exactly is recoverable. These languages have different ways that you can either choose to ignore error or act upon it or panic. But I think we need to think about what exactly are the ways in which we can recover from error anyway. Things that pretty commonly we see retried or recovered from are like network flakiness. Or your database is out of connections. You want to try again later when it has less load. Or your disk is unavailable right now, and maybe it will be in 5 seconds. But in our example, if we have a corrupt JSON dictionary, rereading it 2, 3, 5 times won't really help anything. It's probably still going to be corrupt. And so when I thought about it, the things that we're able to retry cleanly are things that are pretty isolated from what I'm working on. Whoever is writing this JSON-encoded dictionary has a sort of shared state between me and it. And so we're not really perfectly isolated. However, someone else wrote the network stack. They have completely different hardware from my laptop. And so they're sort of forced to both isolate their system and also have a really clear contract between me and them. And I think this is where the microservices architecture also comes from. It forces you to think about exactly what your API is and share as little state as possible between things that don't really need it. The next question is, how do you actually recover? So in our example, I think we need to get rid of really the bad state. And abandonment sort of isolates things at the process level. So it assumes that if anything is wrong in a process, you need to tear it down and start again. Depending on the context of your program, it may be at a different level. For us, probably it's whatever is doing this ID writing thing. So thinking about whatever level of isolation makes sense for you. It could be a request, it could be a thread, it's hard to say. But regardless, you need to make sure that all bad state is cleared away so you can retry. If you leave around the thing that's causing the error to happen in the first place, it's just going to happen again. And so you need to figure out how to clear away what's wrong and get back to a known good point and then continue forward. So here's sort of our set of lessons learned. There are many kinds of exceptions in Python. They're used for a variety of things. Usually the names are kind of indicative of what the exception is intending. They're used for control flow. They're used to show bugs. They're also used to attribute failure in contracts. Speaking of which, when you're writing something that especially is going to be long-lived, you should think about what exactly the contract is of your component. Document the contract using either doc strings, using static type, or you can then therefore use exceptions to attribute breaches in the contract. And then when exceptions do occur in your code, think about when you're debugging exactly what had gone wrong and what assumption was violated at what layer. When you are wanting to self-heal, think about what exactly is recoverable. When you are in the process of self-healing, clear out all of the bad state and get back to a known good point. And I think all of these things, trying to isolate components that do not have concerns with each other is helpful. And all of these things are sort of the best idea, but obviously code evolves over time. And so it's not necessarily going to be the case in all worlds. But these are just places to move towards if you want to achieve the goal of making sure your code is understandable, but also works as you expect it to and doesn't crash unexpectedly. So thank you. You can do questions, yeah. Yes.
Okay, So we have 5 minutes for questions. If you want to approach the microphone over here, remember to phrase your question as a question. Thank you.
Yes.
Sometimes I don't know if I should use assert or throw a value error. And you decided to use assert in your code.
Yes.
Why did
So
you do
there's the tricky thing where, depending on the context in which Python is running, you can choose to compile out assertions. Assertions are sort of supposed to be used for things that you expect never to happen. And generally, when I'm programming, I don't use the -o flag. And so if I'm raising the assertion error, I expect it to crash the program. I think value errors do have this connotation of like the value of something is wrong. So maybe you expect something between 1 and 10, and it inputted 15. That would be a value error. So if you're not using an assertion, then I think thinking about exactly the error type and trying to communicate what went wrong is important. Insertions are nice too because they have that string field afterwards where you can say just like in plain English exactly what went wrong. Whereas when you're raising various exception types, you're assuming the person is able to interpret it.
Thank you.
Sure. Anyone else? Yes?
Hi. When do you think it's appropriate to return none from a function rather than returning the value versus returning an exception?
I see. Returning different things? Sorry, you said function, value, or exception?
Yeah, so when would a function return none, for example, rather than raising an exception?
Yeah. So I think none is really useful for things that haven't been set yet, and you expect them to be later. So it's indicating that like this piece of information will happen later on. I don't think, and that's assuming that you like can, continue going with this piece of information missing. If you sort of think this is not a valid way for the program to run without that information, then raising an exception or crashing is more appropriate.
Okay,
Does that make sense?
Yes, thank you.
Hi. I was wondering if you have an opinion on the idea that it's like idiomatic Python to search for or to see if a value exists in an array or in a list by using like try except for a keyer or indexer.
The more I did research for this talk, the less I was fond of using try except for those kinds of things, looking for values in sets and dictionaries and things. Because most of those sort of, data structures have other ways of checking the existence. If you were to really delve into the performance of it, I think that when things are an exception, they're relatively expensive. Whereas if you do like the if thing and thing check, it's a little bit more overhead every time. So if you don't expect the thing to be in the thing a lot of the time, then like performance-wise, it's probably better to use the non-exception syntax if you like really don't think it's going to happen very often. But like as I said, I'm not really focusing on performance for most of what I'm working on. I just think that like the if item in list check is a little easier to read and a little bit more concise anyway.
Okay, thanks.
Yes. You can just say it to me and I'll repeat it.
So in your examples, you don't wrap the original error string in the malform data error
Yeah.
to bubble it up to the user. Is there a reason for that?
Oh, it was just like me going through and doing things like as if I wasn't thinking about it very much and then seeing the consequences. That is a really good way to continue. So the question was, why didn't I sort of include the original exception in the malform data errors? And I think that's a really good way to maintain the context of where the thing actually came from if you are choosing to use your own custom class. But I don't know, that was just me like going through and doing the first 3 iterations of the program.
Hi. Oh, that's loud, sorry. You mentioned the notion of abandonment. I've been playing with Elixir for the past couple months, and that aspect is really appealing in some cases. Do you think that there's an approach that people can use in Python to abandon an object if something goes wrong, instead of trying to recover and just saying, okay, I'm going to start again later?
That's a good question. The tricky thing about Python is that you can have sort of references to your object or to parts of it that you don't know are duplicated. Like if your object has a list in it and there's another reference to the list somewhere else, unless you've read all of your code super carefully, you don't really know that you've deleted all the references to it. And so that's where I think process level is really appealing, because everything that existed on the process is absolutely torn down. I think there are ways of sort of enforcing boundaries without tearing down an entire process. This is like a sort of interesting question that I'd like to explore more. But maybe, I don't know, there are probably tricky Python language things you can do with like del that would help out.
All right, we are out of time for questions, so please find her later at the conference if you have one. Thank you.